Good morning.
Good time for a resonant circuit. We'll start in a minute. Stream is active, you can stream is active, you can connect.
Yeah, connected. Yeah.
Switch this off.
Good morning, Professor.
Good morning, good morning. Yeah.
I can hear you, you're muted.
And now I'm here. Good morning.
Yeah.
Okay, let's go.
Yeah. Professor, next week we'll see you on campus?
Yeah. We can from the 1st of March, which means tomorrow, we can meet in person. So, yeah, we can.
Perfect, Professor.
But what should I do? We need to inform department. It will be Azanas 12/1 320. My laboratory.
K1 or K2, yeah?
K1
K1.
/1.
Which room, Professor?
320.
320.
Life is better than virtual, no?
Yeah, I think it will be maximum 3 students, I think. We have 3, yeah.
Yeah, we have 3, so it's less than 100.
Yeah. Perfect, Professor, yeah. Let's do that.
So we can. Okay, let's go to see what is a resonant circuit. What goes There. So. Where is my? I can minimize this one. 1 second. I will feel. What I'm doing. 1 second. I feel. This. Okay. Yeah, I got a small experiment. I have prepared a small. Which one? Okay, small experiment. I have a source of a pure sine. Its signal goes as, let's say, as x. We see it here as a yellow line. I hope we see. One nanofarad capacitance, it's not important. Coil of 4 millihenries. 4. It was 4. Oh, 7. Sorry. 7. I took another coil. And variable condenser of 1 nanofarad. 1/2. Output goes as Y. I hope you can see it's a blue line on a scope. Simple experiment, isn't it? Yeah. Wait 1 second. What's something goes. I will disappear. Yeah. And once. Okay, no. Oh! I decided to appear there. So, we have a very simple circuit. Now let's try to investigate it a little bit. myself a bit bigger. What can we see? Frequency, effective value of the input, and effective value of the output, or RMS. And what do we see? Here we have 8.5 millivolts, and at the output 10.9 volts. No energy sources. 1 second, I'll bring camera. Here it is, my circuit. 1 second. Coil. Capacitor, I can change it. And this small box is internal capacitor. It is needed to reduce influence of the generator. I'll explain. I got 11 volts from 300 millivolts. What a gain! Without any energy source. Looks like we have dark energy here. Or energy of the space. Or what? If I change frequency, this effect disappears. If I change capacitance, it disappears, but again is observable on another frequency. Second, I will adjust. I have this ferrite block. Take a look. I'm changing magnetic conductivity of the coil environment. I'm increasing magnetic conductivity. This means I'm increasing amount of the energy magnetic field of coil can store. And you see, effect disappears. What we can say? But it depends on capacitance, it depends on inductance, and it very strongly depends on frequency. Isn't it? Yeah. So, we need to understand what's going on. ask a question. Tell me one thing. How it goes with circuit theory?
We just finished.
We have magnetic circuits last lecture. Introduction to magnetic circuits.
So only introduction.
Oh yeah, yes, sir. Only one lecture.
Okay, no theory of transients.
No,
No, professor. That's one of the last chapters, I think.
Okay, no problem.
By transients, you mean the variable capacitors?
No. When we switch something on or off,
No.
transient regimes.
No. We did one experiment on it, but we haven't done any theory. No.
Did experiment, but without the theory.
Only me, professor, but no one else has done it because I have finished the labs of circuit theory. I finished the labs last semester, but theory I am doing this semester.
Okay, this means what I'll be the first. No problem.
Yes.
Yeah, so let's go. Let's take a look on bit simpler circuit. Let's say we have circuit of active resistance, capacitance, and nice coil. We have something like this. And we have power source. And it's not important at this moment what kind of source will we have. We will try to write down a Kirchhoff voltage law. So, let's write a Kirchhoff voltage law. If E is equal to current multiplied by resistance plus first derivative of current multiplied by inductance and plus sum of all charges, one against capacitance. Here it is. The Kirchhoff voltage law for this circuit. Assuming what flows some current. To solve this equation, we can use different technologies, but the best one is use already solved so-called uniform equation. To convert this equation to the already solved, let's take first derivative to remove this integral. And we have choose or to multiply by capacitance, but more effective is divide by inductance. We will get second derivative of the current plus by L first derivative of the current plus 1 divided by LC current equals to the first derivative of the supplying voltage. Wait 1 second, I'll need to make it bigger. So we have converted Kirchhoff's voltage law to the uniform differential equation. Now, key idea of the transients theory. I'll need to explain it because I'm the first. Let's take, for example, network E F1 switch F2. At the time 0, switch will go on. What will happen? Time. Here we have a 0. Let's say it's at point A, so voltage at that point A as a function of time. What will we see before? Zero. Capacitor fully charged. We consider its insulation ideal. So, it's full charged and current to capacitor is 0. If current is 0, voltage at the A point equals to the source voltage, because voltage drop on the first resistor is 0. So before if now we assume a very long time, infinite time, after the switch. Again, capacitor will be fully charged, but for what voltage? There will be a current through first and second resistor. Voltage at the A point, I will mark it with the infinite index. Will be divided by the ohm law. With the infinite. And what will between them? And between them, capacitor discharge. Such plots are always can be described as an exponent. Can you believe what process will go like this? Or should I assemble this circuit?
No process understood, but with these only discharge, what about the charge?
What's the difference? Charge or discharge? The only difference, discharge goes this way and charge goes... Charge of capacitor goes like this. It will be 1 minus A of the only difference. Okay, now why I'm drawing all this? I need to switch this microphone. Why I'm doing it? For idea. This one, this, let's say, time range is pre-computation. With the blue line, I don't know, it isn't a very blue. So, with the mark on infinity, I have nominated so-called enforced regime. It's let's say, state of the system when all transients are ended, the new stable. And between pre-computation and new stable, we have a transient part. So this one is enforced component, and this one called free component. Enforced component or infinite time regime and free component. Free component or components of the transient. The real transient in our case is U infinite plus free component as a function of time. In our case, it will be E multiplied by 1 minus R2 divided by R1 R2 and E power minus alpha t, where alpha is 1 against R2C, something like this. Let's go back to our circuit. We had source, resistance, coil, capacitance. If something happens here, something changes, free component, not the sum, but free component can be found. We can using an equation, second derivative of the current plus 2 alphas. First derivative of the current plus omega 0 current equals to 0. This equation describes free component. Here introduced alpha is a decrement. It's equals divided by double inductance. And omega 0 frequency. It's a parallel resonance frequency. This equation solved long ago.
Professor, does this apply to any circuit or does it change depending on the schematic?
For any circuit where we have coil and capacitor. At this moment we have one contour. Later I will show what happens when we have couplet circuits. Now we operate with the opposite direction. Let's take a look on a very simple one contour circuit. And later I will expand this knowledge to the system of the couplet circuits. Each contour produces its own free component. We'll see.
So, Professor, it doesn't matter if it's series or parallel or anything like that.
Bit more complicated. But let's go step by step. Now we have first, let's say, very simple approach, one contour. Each contour produces its own free component, its own set of free components. I'll show with examples. Everything is planned. Okay. Important moment. We have an equation. This equation already solved. Free component can be found as I1 a power lambda first time plus I2 a power lambda. This one are constants. I1 and I2 describe or give they are dependent on a circuit state at a computation moment. And lambdas are roots of the so-called characteristic equation. Lambda of lambda plus omega 0 square equals to 0. Solution of this equation gives us characteristics of the free component itself. The full regime consists of free component and enforced or infinite time component. So from the simple mass, we can write what these lambdas 1 and 2 are minus alpha plus minus square root from alpha what I'm doing omega 0 square. To make notation easy, we can introduce a beta being square root of alpha square minus omega 0 square, or another n square root of resistance square quadruple inductance square 1 against LC. So, free component will be decaying process is decaying. Because we have dissipative network. Every network with resistance in any way converts flowing current into heat. That means what? Without outer energy source, any process will tend to the zero. Because supplied energy will become a heat and dissipate in the outer air. So here we have I1 at power beta plus I2 at power should be minus plus no 1. Full current will be free current plus enforced current. Let's take a look on example. DC source E, capacitor C charges from DC source. At a moment time 0, it will discharge and we will have something like this. We will have current. Before computation, before I turn the switch, current will be 0. This means very comfortable. Zero border condition, or zero time condition, or zero pre-computation condition, call it as you want. Also, since the new circuit will not have an energy source, enforced current will be 0. Since at time 0, current will be 0 because coil current can be changed instantly. Is 0 and A equals to minus E. So equals to I on and equals to E divided by double vector A. I want to show this circuit, let's say in nature. I'll use a bit different setup. I'll use generator producing pulses of 1 microsecond each with a frequency of wait, what? Each 2 milliseconds. What I'm doing? I'll use this setup. So every 2 milliseconds my generator will produce pulse of 1.
Professor, can you tell us where I1 and I2 is in the circuit?
I1 and I2 are constants. They are not currents, but constants determine the current. It's a difference. This I1 and I2 are constants. They determine current is I1 a power.
Okay, so from the lambda values we can find.
Yeah. Lambda and so on, okay. What are, I wanted to draw a schematics. What? I will use this setup. Idea, every 2 milliseconds, short 1 microsecond pulse will charge the capacitor, and it after that generator switched off and circuit. I'll use this method. And circuit is free. I need to disconnect. 1 second, I'll bring the generator. I'll bring the electricity magic in. No, this one is. This one goes here. And where is my resistance? Disconnect this one. 1 second, I need to connect the yellow channel. And I forgot to take resistance box. Is my charge circuit? This one. this one is okay. Yeah, resistance box. One moment. Potential. Wait. Resistance box. I'll connect you. Very nice. Nice circuit. Generator, capacitor, coil, and resistance box, two resistance boxes. In series, connected in series. And a bit. Whoa. Okay, let it be as it is. So now, nice circuit with zero border condition. So, free component of current will be minus E divided by double A power better not here multiplied by A power beta time minus A power minus beta time. free component of the coil voltage maybe coil voltage free component will be E divided by double beta A power minus alpha t multiplied by alpha is beta A power beta minus alpha is beta A power minus t. Free component of the coil voltage. Come. 1 second. Why disconnected the terminal? The blue line, this free component, this now is a blue line on a scope. The yellow line of the scope, it's a free component of the capacitor voltage. It is E divided by double beta A power minus alpha t multiplied by alpha plus beta A power beta time minus alpha minus beta A power minus beta time. Wait 1 second. On the previous one, I have plus y minus k. In the previous formula, there should be a plus. Yellow line this is yellow, and the blue line A is
Was that plus in the first one or the second one?
the first one should have plus. 1 second, I will repeat it. It is 0 divided by double beta A power minus alpha. Alpha plus beta A power beta minus alpha plus beta A power minus beta t. It's a blue line. The second one is a blue line. And here, we should consider two possibilities. And it's important in our business. So, one possibility is when alpha is smaller than the omega. Another, alpha is greater than the omega. Or the double characteristic resistance. Rho characteristic resistance is a square root of the L divided by C. Or L is greater than double characteristic resistance. In first case, back is pure imaginary. So back, repeat, which is alpha squared omega 0 squared, will be imaginary, and we will have free oscillation frequency being omega 0 square root 1 minus square resistance divided by quadruple characteristic of wave resistance. Process itself current will be divided by omega Fl. Not enough space. Will be minus A divided by omega Fl. F power alpha sinus omega Ft. That's what we're seeing here. Alpha, this term describes decaying exponent. Here it is. I can switch the time scale. If we connect all these dots, we'll see decaying exponent. What is called Rimsch's constant. Alpha is characterize decay, how energy disappears or being dissipated. And free frequency, free oscillation frequency,
But no say it's negative. The entire equation should be negative.
Negative means the start point. How it starts. At the moment we switch, it's a current. Current flows in opposite direction. Wait 1 second, I will write a voltage. I just want to take your attention to the one moment. Frequency of free oscillation is this omega 0, what we can find from the simple resonance of current, from the simple conditions of resonance of current. Imaginary part of input impedance is 0. But real frequency is bit different. we will have resistance divided by double characteristic square. Wait, wait 1 second, I will switch to and yeah, take a look on the frequency. See, now it's 61 kilohertz. I'm introducing resistance. See, I have increased resistance and frequency become 59. 61. The introduction of active resistance change free oscillation frequency. Why it's important? There are many attempts to search for fault place, to perform a fault location in the distribution network on the basis of the oscillation which occur at the moment of cable insulation breakthrough. The problem is what frequency of such oscillation is dependent on the overall circuit resistance, including resistance at the fault place. So if the fault is not complete, so it is a transient resistance at the fault place, frequency changes and fault location fails. Okay, where we are? I can change scale. What's the effect of the elements? I'm changing capacitance. You see? Frequency changes. I can change inductance. Okay, frequency change. But I would like to change resistance. Here we have decaying signal, kind of decaying oscillations. You can see it's a sine, ideal harmonic signal, but see, it's decaying. Now I will increase resistance. Look what happens. Okay, a bit slower. I'm increasing resistance and you can see at this moment, in fact, we are at a point where alpha is equal to omega 0. It's so-called critical resistance. This one is enough. We have an exponential process. If active resistance introduced is above this critical margin, when alpha is equal to omega 0, we have an exponential process. Below we have decaying oscillation. One of the moments of concern with power electronics is a quality of computation. If you have some kind of inverter and you got process like this, your semiconductor switch will not last. Because high frequency component of oscillation cause hot spots in a structure of semiconductor element, IGBT transistor or what, and fast degradation. If you add so-called snubber, special network, reducing quality of oscillation, let's say, you will have exponential commutation process. It is much more preferable because it causes a much lower load on a semiconductor structure. Another thing I would like to show. I'll switch my scope to the frequency analyze. Okay. Oh, here it is. My scope now performing Fourier transform. See this red needle? It's a frequency analysis of the signal. I'll make multiple. Can you see the red needle? I hope you can. Now all energy is concentrated in the one very narrow frequency band. Look what happens when I increase resistance. Second, I'll bring resistance below the critical process is in a form of a decaying oscillation, and we see very narrow frequency band. Now, okay, where are you? Okay, come back. Yeah, here it is. Now process is aperiodic, and you see the same energy. Amount of energy supplied by generator is the same. But take a look how this energy is distributed. It takes a very broad frequency range. Resonant regime, aperiodic regime. Aperiodic regime, wide frequency range. Resonant regime, very narrow frequency range. The same energy is concentrated That's what we see, is this nice voltage from nowhere. If you attempt to load it, everything disappears. Yes. I can write the pair of formulas. So, free component of the coil voltage will be omega 0 against free oscillation. Of times omega minus some phi. Capacitor free component will be omega 0 divided by free component alpha again sine omega t plus phi. If
so the first case scenario?
Yeah,
Second case scenario.
This one is the first one. When we have oscillations, this one, what we see, what we say. If we have first scenario, our circuit became or maybe called as an oscillation contour. When there are zero losses, its oscillation frequency is equal to the frequency we obtain as a zero of imaginary part of input resistance. Such oscillation systems are characterized with the called decrement, the D being L divided by characteristic resistance, or L divided by square of L divided by C, or L divided omega 0 A. But I think this D isn't known. But it's okay, it's real.
Sorry, Professor, what is D again?
The decrement characteristic. It isn't very popular. Much popular is a contour quality being 1 against D. It's a ratio of resonant voltage or resonant current plus normal non-resonant. We saw 11.5 volts from 300 millivolts. So Q would be 11.5 divided by 0.32. It's a quality of contact. the quality. High quality in our business, 10 or something like 10 is a high quality, really. At the 50 hertz, usual quality isn't high. But in communication, in business of communication, over 400 is achievable. What I'm going to do. We saw what we saw. We saw a frequency depends we can try to use this network. There are two variants. One, something like this. Right? Where all elements are in sequence. Possible. RE, internal resistance of the source. This one in sequence, all elements. One way, another in parallel. This one is parallel contour. I have added resistance. It's one is core resistance, another one to be core. Maybe it's resistance of the wires and so on. We can use resonance effect to create a selective network. Network with a path dependent on frequency. Let's start from the sequence, the connection in sequence. Let's see. E, A, B, and we will have coil here. Resistance and capacitance. Something like this. Input resistance is an input resistance. It will be N plus J omega c. Depending on frequency, it will be inductive or capacitive, but at a frequency omega 0 equals to 1 LC, it will become purely active. It is a resonance frequency. Resistance will fall, will diminish to the active component. Current at the point of resonance will be divided by R. Voltages at reactive elements, coil voltage and capacitor voltage, so at a frequency omega 0, UL will be equal to, and it will be QA. If you have high quality coils and capacitors with the low parasitic resistance for coils and very high insulation resistance for capacitance, you can get quite high voltages. But don't forget what equivalent quality will be characteristic resistance plus internal resistance of the source plus
Professor, what is it minus 1 over omega c? Isn't it plus 1 over omega c?
no, it should be really, it should be plus. Yeah, it should. No, wait 1 second. We need to, it's minus because we need to get G from the divider. Yes, it's minus. It is omega L plus 1 omega C. This way. If we need to take this up, what's mean divide by X? If we have vector X,
Yeah.
this is divided, its rotation in a negative direction by, we can obtain the same operation if we multiply it. See? We will get the same but with the plus sign. And this one is a minus. Now you understand why minus?
Yeah. Okay, but
Complex numbers. They are evil. 1 second. What? Where I was? Sorry, 1 second. I need an overall or equivalent quality. It will be divided by resistance plus source internal resistance plus characteristic square and load resistance. If you want to put a load, get prepared, the effect will disappear. We need to analyze circuit reaction on the frequency. To investigate or make a research in the narrow bands near the resonance, the frequency deviation omega 0 is good, but to compare characteristics often use not absolute value of frequency deviation but relative frequency deviation. It's omega square minus omega z square divided by omega square. Or approximately double frequency deviation divided by omega 0. Such relative deviation is useful when we need to compare network in their, let's say, quality. Also, frequency shift, which is C, being equal omega against omega 0 minus omega 0 against omega. Frequency deviation. Deviation is not a good term. This C, we have a tuned frequency. When the source frequency is equal to the resonance frequency of resonance, we have tuned system. When we shift frequency from this tuned point, we have, say, detuning or shift of tuning. So this shift of tuning in relative values, this is Xi. It's a shift from turning point in relative values. For the small frequency shifts, when frequency deviation is much, or frequency difference is much smaller than the resonant frequency, input reactance, in our case AB, can be written as double characteristic delta omega 0, or it's for small deviation. Imaginary part of the input impedance is approximately characteristic or wave, some call it wave resistance, multiplied by relative frequency shift. Full absolute value of input electrons can be approximated as 1 plus xc squared.
Professor, can we take that break? Until 12:30? That's you sure?
Okay, I'll finish with the characteristic. And we'll take a 15.
Yeah, perfect.
1 second, one formula. So you can approximate ZAB as a rho square decrement square plus epsilon square. Angle will be arctangents of xc, or approximately delta omega divided by omega 0. And characteristic of the current current model against current at the frequency equal to omega 0 will be 1 against square root 1 plus xc squared, or approximately 1 divided by square root 1 plus double delta omega 0 and its square. Yeah, and we can take a small break if you want. How long? Ten, 15 minutes or a minute more.
Schedule says 12:30, Professor. Would be nice.
Half an hour? Yeah. Okay.
Yes, Professor.
Okay, let's do it. So maybe I'll start the second stream to save YouTube
Yeah,
space.
sure, Professor.
Yeah.
It's okay?
Yeah, 10:30. Yeah, okay.
Okay, let's do it. I'll show this characteristic alive.